When we talk about blasting something into space, most of the time you would think they would be using a rocket. But what about using a giant gun? Sounds crazy, but back in the 1960s, a joint project between the US and Canada used just such a giant gun to fire objects into space to test their re-entry characteristics. So, could you actually use a gun to put a satellite or even a spacecraft into orbit?
Curious Droid.
Now, the idea of using a giant gun to fire objects into orbit might seem sound in principle. You only need to send the payload itself without having to carry the massive amount of fuel like a rocket, and in theory, launches could be done in much less time and at much lower costs. But there are several problems, and the first of which was shown over 300 years ago by Isaac Newton. Newton's cannon was a thought experiment in which a cannon is fired horizontally from a very high mountain, so high in fact that it would be above the atmosphere. This was to demonstrate how gravity is universal, and if you got the speed of a cannonball just right, it would end up in orbit around the Earth. Newton himself showed that just like any other parabolic, hyperbolic or elliptical orbit, if you accelerate an object during the orbit, you will always return to the point where the acceleration took place. As our gun is on the surface of the Earth, then the starting point or the firing of the gun is where the acceleration will take place, and this is where our projectile, assuming it's a dumb unguided shell, will return within one orbit. Basically, it will crash back to Earth where it was fired from. The only way to avoid this is either to fire it with such a high velocity that the projectile can break free of Earth's gravity completely and end up in deep space, or once it's reached a suitable altitude, it can correct its course itself and enter a stable orbit like a rocket does. Set up in 1961, Project HARP, or the High Altitude Research Project, was a US-Canadian cooperation headed up by Gerald Bull, that I mentioned earlier. This was to use a large gun to fire projectiles to the edge of space and study their re-entry ballistics in the race to develop intercontinental ballistic missiles, and was cheaper and easier than using either hypersonic wind tunnels or the rather unreliable rockets of the time. The HARP guns were made from 16-inch ex-US Navy guns that were modified by connecting two barrels together to create a total length of 41 meters. One was located in Barbados and the other in Yuma, Arizona. The key feature of these tests was that the gun was oversized and the projectile, a martlet rocket, which was held in a sabu, was undersized. This allowed the test to have the high-speed acceleration. To withstand the huge amount of G-forces during the firing of the gun, which at its peak reached 25,000 G when they pumped out the air in the barrel and then sealed it, the sensitive electronics were potted into a sand and resin mix, which proved to be highly effective in protecting them from the forces of the launch. During tests in 1966, the Yuma-based gun fired a Martlet II weighing around 180 kilograms to a height of 180 kilometers, around 590,000 feet, easily into what is considered space, which officially starts at 100 kilometers and is a record which still stands today. Although this might seem like a lot, the velocity was still only around 2.1 kilometers per second. That's still a fraction of the 7.8 kilometers per second required to reach low Earth orbit. Conventional guns relying upon an explosive charge can only ever reach around 2 kilometers per second, as our projectile can't accelerate faster than the pressure wave from the exploding charge that's pushing it along the barrel. In the 1980s, the Lawrence Livermore Laboratory, as part of Ronald Reagan's Star Wars initiative to shoot down incoming missiles, conducted tests on what they called the SHARP, or the Super HARP gun. This used a two-stage propulsion technique in an L-shaped barrel. Firstly, in a chamber at right angles and at the bottom of the main barrel, a methane air mix is ignited. This pushes a pump piston to compress hydrogen, which then propelled the projectile along the main barrel. As hydrogen is the lightest gas, it can achieve the highest speeds, and in tests, small projectiles reached 10 kilometers per second, enough to achieve orbit. Now, unlike Newton's cannon, which was above the atmosphere, any practical space gun like the Project HARP ones would have to be on the ground, and therefore the projectile would have to be accelerated through the densest part of the atmosphere at hypersonic speeds to have enough velocity to reach an altitude suitable for orbital insertion, and this also brings about the problem of heat. Now, the faster an object goes through the air, the more the air is compressed on its leading edges, and the more the air heats up to a point where it can be well over 1,000 degrees C and cause damage to the projectile itself. As the altitude increases, the air becomes less dense and the heat buildup becomes less till you get to space where it stops altogether. Whereas a rocket starts off slowly in the dense atmosphere and builds up speed through the thinning atmosphere to space, a gun accelerates the object to its full speed during the length of the barrel and right into the dense atmosphere where the air compression and the heat will be at its greatest. Now, before the Soviets put Sputnik satellite into orbit, there was a rumour that the US had accidentally launched an object into space during an atomic bomb test. During the Pascal B nuclear test of 1957, a 100mm thick, 900 kilogram armoured steel end cap was used to seal the 152-metre deep test shaft, and it was welded into place to see if it could contain the radioactive material. When the bomb was detonated at the bottom of the shaft, the end cap was blasted upwards at what was thought to be around 66 kilometres per second, about 150,000 miles an hour. Now, this was actually expected, and as part of the test, high-speed cameras were trained on the cap, but it was only ever caught on one frame of film, so exact figures could not be calculated, but it was said to be travelling like a bat, and probably out of hell. Some believe that it became the first man-made object to be blasted into orbit, but Dr. Robert Brownlee, who worked on the test, believed that it was vaporized by the intense compression heating of travelling through the atmosphere at such a great velocity. But either way, the cap was never seen again. Now, an oversized manhole cover is not the ideal shape for a projectile, and it could be expected to burn up, but with an aerodynamic shape and special heat shielding, the heat issue could be overcome. So we can fix the heating problem, but due to the speed there is also another related issue in that the gun's projectile has an acceleration that's somewhere around 20,000 G. That would turn any delicate satellite into scrap metal and humans into jam, but that didn't stop people from using the idea in fiction or reality. Jules Verne used the idea of a space gun in his sci-fi novel of 1865, From the Earth to the Moon, to fire a manned projectile to the moon. Although many saw it as a work of pure fiction, some of the calculations which Verne did, considering there was no empirical data to go on at the time, turned out to be surprisingly accurate. But the length of the barrel would be the major problem, and would have to be incredibly long if humans were to be passengers inside. In order to launch humans into orbit and onto the moon, like in Verne's story, the maximum acceleration you'd want to subject your passengers to would be about 7G, though in the space shuttle it was around 3, and in Soyuz it's 4.5. So to be on the safe side, you're probably looking at less than 5G for longer periods of time. The length of the barrel, if you allow the acceleration to increase safely from 0 to 7.8 kilometers per second, would need to be greater than 50 kilometers long, depending upon the level of G you were going to inflict on your passengers. This pretty much rules out any conventional gun powered by an explosive charge, but an electromagnetic railgun could start at a much lower speed and reach top speeds high enough to reach orbital velocities. This idea has actually been proposed to launch payloads into orbit which are not affected by the high G-forces, such as food, water and fuel. But even limiting the acceleration to 1,000 G, it would still require a track over a kilometre long. With current technologies, this would be very challenging, but not impossible. The biggest issues being the arcing of the electrically conducting track and the sabu, and the atmospheric heating of a projectile at hypersonic speeds. Coil guns, which use high-power electromagnets to propel the projectile with no physical contact, would eliminate the wear on the tracks, but aren't currently capable of reaching 7 kilometers per second. The best launch sites would be near the equator to take advantage of the Earth's rotational speed, and 2 to 3 kilometers up the side of a mountain in less dense air and where noise would not be an issue. This would still rule out transporting delicate satellites and humans, but could dramatically reduce the cost of getting raw materials into orbit. So it looks like rockets will be with us for the foreseeable future, if only to get delicate payloads into orbit, unless, of course, we can build a space elevator. But that's a whole other story altogether. And in which case, don't forget to check out some of our other videos, and please subscribe, rate and share.